going back to the lecture, we're finally on that, or at that point in chapter 5, where I mentioned to you that chemistry gets a little wacky, a little crazy. And it's not so much chemistry, but chemistry combined with physics. So in some ways, chemistry talks about matter more than energy, but it does need to have an understanding of what energy is all about to explain the behavior of different atoms. So when you look at the periodic table, I mentioned to you last week that unlike real people, elements, which I sometimes think of them as little people, like to mingle with each other. And they are very particular because the elements on the far left try to mingle with elements on the far right, and vice versa. And elements within the same group do not interact well with elements on that same group. They rather interact with elements on the other side of the table than with their own. It's just the way nature works. But there's an explanation for that, and that explanation resides with the tiniest of all particles that we study in this course, the electron. Now, in the chapter last week, we talked about something called the electromagnetic spectrum. And I did not elaborate too much, and in fact, I don't want to elaborate too much today. Simply, I want you to be aware of the fact that energy travels through space as a wave. But there's many different kinds of energy. Some energy forms include things like radio waves, the stuff that your cellular phone is using to communicate with other cellular phones. So those have long radio waves which actually carry less energy than other electromagnetic forms of energy like X-rays, which are going to be shorter wavelength, meaning the energy that they pack is much higher. One thing to remember about this graph is that the relationship between the wavelength, the distance between one valley, one bottom, and the next bottom, or one top, one peak, and the next peak, is greater in what we call long wave wavelengths. The energy is inversely proportional to that. So the amount of energy on longer wavelengths is lower than the amount of energy in the shorter wavelengths, which is going to be greater. Now, visible light occupies a very tiny space in this spectrum. The numbers that you see here are actually measurements. So the wavelength is measured in meters, but you can see here how it goes from 10 to the fifth, almost a million meters, to all the way 10 to the negative 11, almost like a trillionth of a meter. So there's a wide variety of wavelengths. But what is interesting to us right now is all of these forms of energy can be classified as something called a photon. So a photon is the way in which energy is packed. So it's a package, to put it one way, of energy. But there's all kinds of photons, just as there's all kinds of wavelengths. So photons here have a different behavior than photons here. Now we're going to look at photons in the visible spectrum just to try to explain what we can see. Now for that, please bear with me, and I'm going to draw a simple cartoon of a very basic element, the most basic of all elements, and that is hydrogen. So I'm going to draw a circle indicating the nucleus of that hydrogen atom, in which you find the one proton that you know exists. We already talked about the nucleus containing protons and neutrons. in this discussion, we're just going to talk about the one proton of hydrogen. Now, the star of this chapter is the electron. It's not the proton and it's not the neutron. It's actually the electron. If you remember, the number of protons determine the identity of the element. One proton, hydrogen. Two protons, helium. Three protons, lithium, so on and so forth. The number of electrons, what happened here? The number of electrons is equal to the number of protons up to a point. And we're going to talk about in the next chapter how that is actually not always the case. In fact, in Lab 6, we also begin to explore the idea of a different number of electrons and the number of protons. But the identity doesn't change regardless of how electrons come and go. Now, having said that, hydrogen has only one electron, right? One proton, one electron. We're going to give it a provisional home in something that I have drawn here as a circle, a bigger circle than the nucleus. And I'm just going to place it for, I guess, for visualization, if you will, right there. We really do not know where the electron is, but we can guess that it's somewhere in this vicinity. Why is that important at this point? Well, because I want you to understand what is the relationship between electrons and photons. And for that, we're going to create another area where the electron could be found. It's not likely to be found there, but it could be found there. And then yet another area where the electron could be found. Not likely, but it could be found. It's not impossible, in other words. These different areas have different energy content, energy levels. Now, the electron likes it here, closer to the nucleus. At that location, the electron has the least amount of energy in it. So it's said to be on the ground state. However, when a form of energy from outside comes and excites the electron, I guess exciton, attempts to move it, the electron sometimes in fact jumps from one energy level, the one that is most likely to be found, to the next energy level. So this electron now could be found here. Or if that excitement is so high, it could actually jump all the way to here. It's the same electron. There's only one electron. Now, what happens is that that electron, which is now all excited because there was some energy that kicked it out of here and pushed it to a higher level of energy, wants to go back home. And when it goes back home to the first level, it releases that energy that it had. So it's now calming down and coming back home. That release of energy is in the form of photons. Okay, that's what the photons are. So it's an energy burst from the electron in the form of a photon with different energy amounts. Now, these are packets of energy. They exist in, what's the word that the book uses? Not distinct, but, oh my God, not continuous either. Let me show you here the image that the book uses. Discrete is the word that I'm looking for. Page 129. There's a really good analogy right here. So the packets of energy exist in discrete levels, like shelves on a bookcase. If you think of a book as a photon, well, you know that a book can be placed on the first shelf. It can be placed on the third shelf, on the fifth shelf, but it cannot be placed in between shelves. So that's what we talk about when we talk about discrete amounts of energy. There's no such thing as 1.5 photons. There is either 1 photon, 2 photons in those packages of energy. So now that this electron is trying to come back home, in doing so, in coming back home, it releases that photon or those photons of energy. And those have different color when you analyze them using a glass known as a prism. Different elements produce different colors of photon excitement. These are almost like fingerprints for different elements. All of those lines represent one electron jumping to a higher level, or a highest level, or a level in between, and then coming back home. Yes?
Does the bookshelf analogy also apply to the energy that's released? So like if a book on the top shelf falls off the shelf, it's going to fall with a lot more energy than one released off.
Absolutely correct.
So I actually didn't know if it jumped from a higher shelf to a lower one.
Correct. That's exactly, so if this is shelf 1, and that electron is a book, and I move that book to the third shelf, that electron actually can come back to the second shelf. But it's not home, so it's going to try to come back to the first shelf all the time. Now, this is the simplest case. This is with hydrogen. There's only one electron. There's many shelves in the bookcase, but there's only one electron. That one electron always wants to be home, and that home happens to be the first shelf, the lowest energy shelf on that bookcase. Now, I don't use the bookcase analogy very much in my explanation. I use more like an apartment building analogy, and that's what I'm going to use probably today. But they achieve the same goal, which is to understand that electrons can only be in fixed levels of energy, not in between levels of energy. Okay, now with that said, let's talk about how many energy levels are there. So this is the atom of hydrogen. I put here 3 levels of energy. Are there more? Yes. There's a 4th level, there's a 5th level, but the likelihood of that one electron of hydrogen moving all the way up to the 5th level is very, very, very unlikely. It's not going to happen often. So with 3 levels, we have enough for a good explanation, or at least a beginning explanation of what happens to that electron. Now, things are not that simple, however. We need to start looking at this cartoon in a little bit more detail. And for that, I'm going to use the first 3 elements to explain what I use as my analogy, which may not be the best, but is the one that has worked for me. So here I'm going to draw a line that indicates the bottom floor, the ground level, of 3 different buildings. Each of these 3 different buildings is one different kind of atom. So the first building is going to represent hydrogen. The second building is going to represent helium, the second element on the periodic table. And the third building is going to represent lithium, which is the one with 3 protons and 3 electrons, the third element on the periodic table. Now, all of these buildings have multiple floors, just like a bookshelf has multiple shelves. However, the structure of the building is kind of weird. The very first floor of this apartment building has only one apartment. I don't know if that's a good visualization or if you can visualize this, but you know, you've seen buildings with apartments, and most of those buildings have the same rectangular shape. You have 10 apartments on the first floor, 10 on the second floor, 10 on the third. This is a strange building with only one apartment on the very first floor, And we're going to call that first floor the first floor. So level 1. Now, it turns out that that first apartment has room, space, for only 2 electrons. You cannot put more than 2 electrons in that first apartment. That's not a problem for hydrogen, because hydrogen has only 1 electron to give it a home. So we're going to put that 1 electron here, and let me put it as an arrow pointing up. So that arrow represents an electron belonging to hydrogen, and is found on the very first level. Just as I said before, the second level exists, is there. That's where that electron can move up if it gets excited. But that second floor is bigger. And it actually has 4 different apartments of 2 different kinds. So the first floor has just 1 type of apartment. Let's call it the studio apartment. The second floor has 2 different kinds of apartments, but it has 4 apartments. So I'm going to divide this into 4 spaces. 1, 2, 3, 4. 1, 2, 3, 4. So on and so forth. That's the second level. Now we're going to call these the S, actually lowercase s, type of apartment. So this is S, this is S, this is S. The second floor of all atoms, including hydrogen, which only has 1 electron, has also an S type of apartment. But then it has 3 apartments, all of them very much the same layout, maybe with windows facing in a different direction, but the same size, the same arrangement, and we're going to call those P, letter P, small p if you will. So this is S, this is P, this is P, and this is P. Now if we want to distinguish them, and we don't have to in this course, but if we wanted to distinguish them, some books call them PX, PY, and PZ as the last 3 letters of the alphabet, X, Y, and Z. I'm not going to distinguish them here. It's not necessary. Just keep in mind that there are 3 P apartment types. In a minute, I'm going to draw the next level, but right now let's concentrate on these first 2 levels. So hydrogen, 1 electron, that 1 electron resides on the very first floor on the apartment type S. Helium has 2 electrons. Well, just as hydrogen, the very first electron likes it in the first level, apartment S. The second electron, which I'm going to describe here as an arrow pointing down, also likes it in that same apartment. So the 2 electrons of helium, helium is atomic number 2, so it has only 2 electrons, reside on the first floor of this building on apartment S. They live together. And that's that. We don't have any more electrons to give a home. Lithium has 3 electrons. And here comes one rule that you have to remember, because it's an important one. Lithium with 3 electrons is going to place the first 2 electrons just as hydrogen and helium did. The first and only electron of hydrogen behaves in lithium just like that. The second one just like in helium like that. But now we have a 3rd electron. So a rule that you have to remember is that in the very first floor, in the apartment type S, there's only room for 2 electrons. There's no more space. We call actually that the duet rule. So the first floor has this rule that only 2 electrons are allowed in that very first floor in the type of apartment known as S. So the third electron of lithium has no chance of being there, has to move to the next level. Now, the electron that we have left to give a home could go here or could go into any of these 3p apartments. Well, there's another rule. The way I drew this is not exactly accurate. S has a little bit less energy than P. In other words, it costs less. It's cheaper. Okay? So the electrons are going to go to the cheapest room. The third electron of lithium is going to go to this room, which now has a name because it's on the second floor. It's called the 2S apartment. Now we can use this information to write something called an electron configuration. This is nothing but the address of all the electrons in an atom. So the electron configuration of an atom is going to be your main task in this chapter, to find a home for every electron in different kinds of atoms following some rules. We're going to abbreviate the home of the 1 electron of hydrogen as follows: 1s1. Okay? The very first number represents the floor, the energy level. The S represents the type of apartment, and this 1 represents the number of electrons living in that apartment. Okay? So let's do the same for helium. So helium still has electrons in the first floor, but both electrons are in the same apartment, so we're going to put them as a 2. That's not a square, it's a number 2, meaning there are 2 electrons on that S apartment. So the home of that is 1s2. For lithium, well, the first 2 electrons, because it's cheaper to live on the first floor, are going to be on the first floor. So they're going to be just like helium, 1s2. But there's a third electron that we need to give a home, and we need to be able to express where that home is. So it's now on the second floor, on the type of apartment called S, but there's only 1 electron. So the electron configuration, the address of the 3 electrons that live in lithium, is known as 1s2, 2s1. Now, of course, it's not as simple as 3 electrons. If you come over here and you point at any element away from those 3, I could choose magnesium with 12 electrons, or I could choose oxygen with 8. Let's move to something a little bit more crowded, such as oxygen. So this is now going to be oxygen. Let's see where those electrons live, because in the process, we're going to learn some new rules. So oxygen is atomic number 8. That means it has 8 protons, and therefore it has 8 electrons, right? Let's give them the home. So we have 8 electrons here. And we need to start just as we did for the first 3. The first 2 are going to be here. The third one right here. Now what happens to the fourth one? Well, the fourth one, and here's where it becomes a little more complicated, is going to go still here because there's still room there. Okay? Now, it's cheaper to put the electron, in this case the fourth electron, on the 2s level than on the 2p level, because it's a little bit lower energy. So that's why it goes there. But we have only 4 electrons placed. We have 4 more to go. Where do they go? Here is a new rule. The 5th one, well, you guessed it. Every room of the S-type has only room for 2 electrons. There are 3 apartments of the type P. Each of those 3 apartments has room for only 2 electrons. So the 5th one of oxygen is going to go here. So now we have 1, 2, 3, 4, 5 electrons. We have 3 more to go. What am I going to do? Well, I could say, oh, let me fill this apartment with another electron and put it there, but that would be wrong as far as we know. You know, this is all in the imaginations of some crazy chemist. But these crazy chemists tell us that there's another rule that we need to remember. As long as there's space on the apartments that are of the same energy, of the same cost, rather than putting a second occupant on the same room where the previous one went, you need to occupy the ones that are empty. That's the way electrons like it. So the 6th electron is going to go here. And the 7th electron is going to go here. Now let's count. We have 1, 2, 3, 4, 5, 6, 7 electrons, but we need to find a home for 8. Well, now there's no choice because now all 3 of the p-type of apartments have 1 electron, but to pair them. And it really doesn't matter where you put it. I could put it on the middle one, I could put it on the end, I could put it on the left. Just to be logical and maybe a little bit more sensible, if you will, let's just work left to right the way everything works in the Western world. So I'm going to put the 8th one on the first P room, pointing down just because that's the way I decided to show you these different electrons. There's a reason for that, but we don't have to worry about it. So now if we count the arrows that I have 1, 2, 3, 4, 5, 6, 7, 8. 8 total electrons. Let's write the electron configuration for oxygen according to where these different elements are, different atoms are located. So we're going to start. First floor. First floor, apartment S, 2 electrons, right? That's the way we have written it for helium, lithium, and even for hydrogen, but there was only 1 electron there. So now we go to the second floor. What do we have? We have a second floor with an apartment type S with 2 electrons. But then we have electrons on apartment type P on the second floor. So we're going to say 2P. And here's another rule that you had to remember. I could actually write 2px, 2py, 2pc, but it's getting too complicated, too cumbersome. So we're going to combine the 3 apartment type P for the electron configuration only into 1 single P. And we're going to count how many electrons are in the P apartment type on the 2P level. And we happen to have 1, 2, 3, 4. So we're going to put a 4. So the electron configuration of oxygen, the home for every electron in oxygen, is given by the 1s2, 2s2, 2p4 electron configuration. That's the home of all 8 electrons. Now, it gets a little bit more complicated than that, and we're gonna simply use a drawing that is going to help us with this drawing, with this writing. So let's take a look at this image. We are on level 2, second floor, and we know that there is a type of apartment known as S, 3 known as P. Now what happens when we have more electrons? In essence, what I'm telling you is that in this second floor, there's still room for 2 more electrons, right? One here and one there. When we get to that, and we need to place 1 more electron, we have a situation that we have to discuss. Let's take a look at the one that occupies every room on the second floor and what that looks like. So for that, I'm going to go to periodic table and go to neon. Neon is on the far right on the group known as 18, the noble gases, and it has 10 electrons, 10 protons, 10 electrons. So let's do that here. So that's neon, Ne. We need to find a home for 10 electrons. The first 8 are just going to be like oxygen. There's no 2 ways about it. So we're going to put 1 there and 1 there, 1 there and 1 there, 1 there, 1 there. So that's the 8 that we have here. We have 2 more electrons to give a home to. Well, there's 2 more spaces, 1 on this one and 1 on that one. So there goes 1, there goes the second one. And now we have all 10 electrons with a home for neon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Electron configuration, 1s2, 2s2, 2p. How many do we have on p? 1, 2, 3, 4, 5, 6. So another rule that you're going to be remembering almost automatically is that the p level is full, is completely packed with 6 electrons. There's no more room because there's only 3 p apartments with room for 2 electrons each. 2 plus 2 plus 2 is 6. That's it. Now there's something interesting beginning to happen here. Oxygen, in its electronic configuration, in its apartment building, has room for 2 more electrons there. There's 2 rooms with 1 empty spot each. Neon does not. The neon is at full capacity. First floor is packed. Second floor is packed. There's no more room. Well, this is what makes neon happy that way. And this is what makes oxygen not too happy because it wishes to fill those 2 empty spaces with electrons so that the cost of every appliance that is running there, the cost of water, the cost of everything that goes together is equally distributed among 8 occupants on the second floor. And it's not like that. So oxygen is always looking for 2 electrons somewhere to fill those 2 spaces. Oxygen, when it finds those 2 electrons, remains oxygen because it still has only 8 protons. It may have now 10 electrons, just like neon does, but it's still oxygen. When we get to that level, we're going to be talking about ions because there's going to be now a different number of protons when compared to the number of electrons. Now let's go back and do one more level, and I think that's where we're going to quit. So let's put the 3rd floor on this apartment building. And of course, we're going to be looking at different elements because now we're going to have to look at some of those wacky rules that I was telling you about. The 3rd floor is bigger. I don't think it's going to work, so I'm going to leave it just on this one. So the 3rd floor has also an S apartment type, 1, 2, 3 P apartment types, but it has a new type of apartment that we're going to call the D type, D as in David. And there's 5 of them. So 1, 2, 3, 4, 5. So this is S, this is P, P, and P, and these 5 are called D. and it's the third floor. Now, just as the first and the second floor, S can only accommodate 2 electrons. Just as the second floor, P can only accommodate 6 electrons, 2 on each of the 3. So D, just as before, each apartment can only accommodate 2 electrons, but there's 5 of them. So on the D type of apartment, you can have a grand total of 10 electrons, 2 times 5, right? 2, 4, 6, 8, 10. Believe it or not, that's it for the third floor. There's only those 3 types of apartments. The fourth floor has a new type of apartment called F. Now the F type of apartment still has several apartment type Fs with 2 electrons per apartment type, but it has 7 of those. So there's a total of 14 electrons that can live in the type of apartment that we're going to call an F. And then if we move to the 5th floor, which does exist, you're going to have S, P, D, and F, just like on the 4th floor. And then there's going to be G with even more space. But let's just do a quick exercise here. In this chemistry course, we're interested in mostly biological important elements: carbon, oxygen, nitrogen, sulfur, phosphorus, hydrogen. That's about it. Those guys are not found beyond 20 protons, 20 electrons. So let's see where they would have their electrons if we needed to find them at home. So let's count. 2 plus 8 more is 10, plus 8 more is 18, plus 10 is 28 electrons. Now we are way past the 20 that I mentioned to you. So the important biological elements live in apartment buildings that have only 3 floors or below. When we get to stranger and stranger elements, even things like gold. Well, let's see, gold, AU, where is that? I always have a hard time. Oh, thank you. 79 electrons. So how many of these would we need? Well, we were here at what? 2 plus 8, 10, plus 8, 18, plus 10, 28. And then, oh my God, probably at this level we would be filling gold. We wouldn't even need the 5th floor. And actually, there is a way of telling that, and I'll show you that very soon. Because now we can follow the arrow the way it goes. So you go 1s, 2s, 2p, 3s, 3p, 4s. You don't go to 3D as you would logically think, because it's on the same level. No, you skip 3D, you go first to 4s, then you go to 3D. And then after 3D, you don't go, as you would expect, to 4s because you already were there. You go to 4p, then 5s, then 4D. And this is not even infallible, by the way. It still can make mistakes for a couple of elements there that are very, very weird. But this will give you, most of the time, the correct electron configuration. We'll put it to a test in a minute. Just bear with me for a second. Now, that's a lot of information in just on their, 45 minutes. So let's take a pause and ask ourselves a question. How good is the periodic table at helping me with this? Well, let me see if I can show you how good that is. It turns out that if you look at the periodic table, and very importantly, you look at the period number. The period number is the floor where the highest electrons in that element are going to reside. So period 1, hydrogen and helium. The 2 electrons of helium are on the first floor. That's what the period 1 is telling me. let's take a look at, for instance, the level 4. It turns out that any element on period 4, potassium, calcium, etc., is going to have electrons on the 4th floor and no higher than on the 4th floor. So the period number tells you where are the highest electrons, how many apartments are occupied in that particular building. So potassium doesn't have a 5th level occupied. It only has electrons on the 4th level. Now, the group number also is helpful, because for the first 2 groups and then the last 6 groups, 13, 14, 15, 16, 17, and 18, you see the number of electrons on the S and the P levels. So let's count. How many columns are on the first 2 groups? 2, right? These are S electrons, meaning the highest electron in these 2 atoms on these 2 groups are going to be found on an S level. I'm going to make a prediction. Let me look at calcium, for instance. Calcium has 20 electrons. So we're going to write the calcium electron configuration. 20 electrons. Because calcium is found on the 4th period, I'm going to predict that the last floor on calcium is going to be the 4th floor. Because calcium is on group 2, I'm going to predict that there are 2 electrons on that highest level, and that is going to be S, because it's the first 2 columns. So S2. That's going to be the highest level of electrons. Now, let's fill the first 3 floors and see if we, in fact, account for 18 electrons, because now I'm taking a gamble and telling you that those 2 electrons live there. Well, 1, 2, 2, 3, 3, I believe. Okay, so 1s2, first floor, 2 electrons, 2s2, 2p6, then we go to 3s2. Now let's take a look at the cheat sheet here. After 3s, we go where? We go to 3p. So let's go to 3p, just as I wrote it here, 3p. And I'm going to put 6 electrons there. Now, why 6 electrons? Well, because I'm taking a gamble and telling you that the highest floor with electrons is going to be the 4th floor. So therefore, the 3rd floor must be completely full. And there's a maximum of 6 electrons on the 3rd floor. What happens after 3p? What's the next level? Oh, 4s. And that's where we are. Okay? Let's count electrons and see if this is calcium already. 2, 4, 10, 12, 18, plus 2, 20. So we were able to predict that from the periodic table. Group 4, block S. So we're going to call these to the S type of apartment. Well, what about the P? If you don't mind, I'm going to squeeze through here. The P goes from here to here. Maybe blue. I guess somebody else has written before me. So we can always erase it. From here to here, all of these are known as P block electrons. And you can make predictions, again, just by looking at that. What comes after P, we said it was D, right? D are going to be from here to here. So these are D electrons. And then after D, we said F. Those are going to be here. Now there is G, and those guys are weird because they don't even exist very long. They exist for fractions of a second, but they're going to be there. Now, the good news is that I don't want you to worry too much about electrons on the F type of apartment, but you should be able to give home 2 electrons on S, P, and even D. Now, one last complication, if you will. That has to do with the shape of the actual apartments. The shape of the S apartment is like a circle, is spherical. In 3 dimensions, it's a sphere. So let me show you. The sphere. So is this space here. Now all of those little dots are just probability. The darker the area, the more probability for an electron to be found there, the lighter, the less of a probability. We don't have to worry about that too much. You should know about the shape. Now, it turns out that as you go higher and higher in energy, that shape is a little bit bigger. It's not that the room is bigger, but it's the fact that the probability of the electron being found not only close to the center, is it actually probable to be found here, not always there. That's all he's saying. The room is still the same room as before. There's only room for 2 electrons. Okay? Now, what about the P type of apartment? What shape does that have? Well, you see, it gets a little crazy. It's like a, I don't even know, a figure 8 shape, dumbbell, one of those things that you use for weights. So what does that tell you? Well, that the probability of the electron to be found here is going to be higher than to be found there. But it's probably not very likely to be found here at all. It really doesn't matter to us. But to the quantum chemist, to the chemist that studies this from the physical point of view, it matters. The D ones are even stranger. I mean, they're pretty cartoons, but you know, to us, they're not going to be that significant. Now, is this useful at all? Well, in a minute, we're going to start answering questions from the homework. But I want you to consider the following. We're going to draw the electron configuration for 2 atoms. And then with that, we're going to move to the homework. We're going to pick sodium as one of the 2. And then we're going to pick chlorine as the second one. And let's do the electron configuration for both. So here we go, sodium, Na. Oops. How many electrons are in sodium? Well, let's take a look at the atomic number, 11. So there are 11 electrons that we need to give a home to. Now let's make the prediction. Sodium is found in period 3 and is found in group 1. So I'm going to predict that the very last occupied space is going to be 3, that's the period number, S, because it's in the first 2 blocks, and then it's on group 1, so it's going to be 1 electron. That's my prediction. Let's go to chlorine. So chlorine, atomic number 17, correct me if I'm wrong. So there are 17 electrons. Well, what period? Still period 3. So I'm going to predict that the last level with electrons is going to be the 3rd floor. Now, where is it found? It's found in group 17. but it's found in group 17, which is in block P. And if I look at the all numbering system, I see that that is called 7 also. So 17, 7, what is that telling me? Well, let's break the block P into the orbitals that can exist. So we have 1, 2, 3, 4, 5, 6 electrons, right? So the first 2, the second 2, the last 5 and 6. So there are 5 electrons in the P level, right? How am I counting that? Well, I'm counting from where the P level starts, 1, 2, 3, 4, 5. So the group number didn't help me much in this case. But the position in the P block is telling me that there's got to be 5 electrons there. So I'm going to say that, of course, there are electrons on the 3s because it gets filled up first. And then there are electrons on the P, and there's 5 of them. Now the group number now seems to help a little bit. This is group number 17. If we only think of the second digit, 7, that's where this 7 comes from. 5 plus 2, 7. All numbering system 7A. New numbering system 17. So the second digit tells me that there are 7 electrons. That's my prediction. Okay, let's put the other electrons on the lower level. 1s2, 2s2, 2p6. According to our diagram, after 2p6, we go to 3s, and that's what we have there. Now let's count electrons. 2 plus 2, 4, plus 6, 10, plus 1, 11. That's it. So we got the electron configuration of sodium right. Chloride. Well, let's go before 3s. We have the same scenario as in sodium. 1s2, 2s2, 2p6. And let's count. We have 2 plus 2, 4, plus 6, 10, 12, and 5, 17 electrons. So this is the correct electron configuration for both sodium and chlorine. Now, if we had this with the blocks, if we had this with the floors, I don't even know if I have enough, but let's take a look at what happens here. So we have 2 electrons here, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That would be in a cartoon form where all the 11 electrons of sodium would be. First floor, second floor, third floor. 3s1. This is S, P, 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 D, 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 D. Let's take a look at chlorine. First floor, second floor, third floor. 1, 2, 3, 4, 5, 6. So this is S, P, 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 D, 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 D. Let's put the electrons. There's 17 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay? If you count, we have 17 arrows. Importantly, how much more room is there on the third floor on the type of apartment P, how many more electrons can we put there? Only one more, because P gets full with 6, 2 plus 2 plus 2. How much more room is here in the third level of of sodium? Oh, there's plenty of room. 1 there, and then 6 here, plus 10 there. There's plenty of room. Well, this is where the fact that sodium and chlorine, being in opposite sides of the periodic table, like to make an agreement, like to make a partnership. Let's take away this electron just for a second. So this electron is going to move out. Now, I have to find a home for that electron that I'm evicting, if you will. Well, that electron, sodium, last electron on the third floor, is going to make an agreement with chlorine and say, you know what, I'm going to pass you that electron, which is just occupying an apartment there and not using all of the utilities wisely. Why don't you accept it? So he's going to come over here, and he's going to end up right there. Chlorine is going to say, okay, I'll take it. So I'm going to put it here temporarily, thicker. That came from sodium. Chlorine accepted it. Let's see what has happened here. So if I erase this electron, because he moved over here, what do I have? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons instead of 11, right? Is that making sense? You're losing 1 electron. That electron is going to chlorine. Keep that in mind, because we're going to do some arithmetic in a second. How about chlorine? What's the scenario for chlorine? Well, chlorine had 1 empty room in the apartment 3P, and it allowed the sodium electron to occupy that space. So if we now count, we have 2 plus 8, 10, 12, 14, 16, 18 electrons instead of 17 electrons. So this guy has now 18 electrons as opposed to the 17, and this has 10 electrons as opposed to the 11. So here comes the arithmetic, and you're only going to get good at this as you practice the problems. So in the beginning we said the number of protons and the number of electrons is always the same, right? With some exceptions. Well, here's one exception. When sodium, in an effort to be happier, gets rid of 1 electron, it remains now with 10 electrons. It's still sodium, but now there's a difference in the charges from the 10 electrons and the 11 protons. The protons are positive. So what happens if I add 10 minuses, 10 negatives, to 11 positives? What's the grand total of that arithmetic? So the result of this is a surplus of 1, plus 1. What happens if I do the same with chlorine? This time I have 18 electrons, but I have only 17 protons because chlorine is still chlorine. So if you do the arithmetic, you have 18 minuses or negatives and only 17 pluses. What's the grand total, arithmetically speaking, or negative 1? So you have a deficit of 1, but it's a negative 1 charge. That means you have 1 more electron than the number of protons. This chlorine atom now is not chlorine per se. It's still chlorine personality-wise, but we're going to call that chloride. And that's an ion. This, we are not going to change the name, but we're going to have to call it something. So we're going to call it sodium, and we're going to append the word ion to it. sodium ion. If you say chloride ion is fine, but chloride, changing the ending, implies an ion. So if I change the ending from INE to IDE, then implies an ion. You can certainly call it a chlorine ion. Why not sodiide? Don't ask me. Ask the chemists who came up with this naming, and that's the way they like it. So we're going to respect their wish. Now, sodium is still sodium, but now it has a charge of +1. Chlorine is still chlorine, but it has a charge of -1. Both of these elements now are happy because they have full occupancy in the highest occupied level. More importantly, they look like a member of the elite of the noble gases. Electron-wise, they look like members of group 18. If you don't believe me, let's take a look. So let's take a look at chlorine, which has 18 electrons. Well, what element has 18 electrons naturally? Well, the element with 18 protons, right? So what is the element with 18 protons? Argon. So if we draw the electron configuration of argon, that electron configuration is going to look like this. 1s2, 2s2, 2p6, 3s2, 3p6. I haven't corrected this, by the way. The electron configuration of chlorine is still 3p5, but the electron configuration of chloride is 3p6. I mean, that extra electron that I added here has to go somewhere. So chloride has the same electron configuration. The electron from sodium that came in here makes this a 3p6. So it looks like that. So chlorine is still chlorine, but it now can brag that it has the same number of electrons as a member of the elite of the noble gases. It's almost like it got admitted to the club. Not really, but kind of. Okay, so what happens to sodium? Well, sodium starts with 11. If it loses 1 electron, then it has 10 electrons, right? What element in the periodic table has 10 electrons naturally, 10 protons? Neon. Also group 18. Also a noble gas. So if we draw the structure, the electron configuration of neon, we have 1s2, 2s2, 2p6. And that's what this guy ends up when it loses that 1 electron. So if sodium loses 1 electron, that one in the highest level, now it looks like 1s2, 2s2, 2p6, 1s2, 2s2, 2p6. It looks like neon is happy. That's what all elements are going to try to do. Gain or lose electrons just so that they look like members of the elite of group 18. I know it's a heck of a lot of information for one session, but it's going to become a little bit easier to manage once you practice some of the problems. Now, in chapter 6, we're going to talk about something called the octet rule. So this was a duet. We also have an octet or octet rule, and that means 8 electrons. But we'll get there when we'll get there on chapter 6. At this moment, unless you have questions, I want to open the homework and start looking at some of these questions. We don't have a lot of time left, but give me just 2 minutes. There's no homework ready? Oh, no. Well, let's fix that. Yeah, so let's fix that.
I never saw the homework 5. We never got it. Oh, did you?
You're absolutely right. You're absolutely right. I haven't even opened it. So I'm going to open it right now. Okay. Let me fix that right now. Now, everyone, I need your attention just for a brief minute here.
Yes.
Remember that I'm putting the deadline now as the end of the semester, just to make things easier to those of you who run into emergencies and cannot find it on time. Because I often get emails in my online course, I try to keep these deadlines more fixed. And of course, somebody misses exam and the system auto-grades giving a penalty if you finish this after the deadline, and you start panicking because you have 0 when you completed the entire exam. Well, to avoid that, I'm just going to put this as, and here is where the problem arises. So check, this is what I do behind closed doors, whatever. So there it is, December 12th, but it automatically makes an available date of December 5th. By default, only 1 week. So I had to change that. It's not a big deal, but I had to change it and be mindful about it. So I'm going to change that to today, but then I'm going to move it to the 14th because it always goes with the midnight deadline. So now, very soon, it's going to be open to you. Okay, so let me do that just for the quiz too, and then we'll open it. The reading is always available, but for that I'm going to keep the deadline within reason. So I'm going to go to October the 27th. That's hopefully by when we're going to be completely finished. And then the tutorials should be also available for those of you who like to practice with them. Okay, so now I have to save that. And let's open the homework. If it doesn't show automatically, just give me until this afternoon when I get home, and I'll add them to the list of assignments. Because that has to be added to this list. And I don't want to bore you with how it doesn't automatically show up. Let me do one. Just give me 1 second. Let me just fix that one. Nope. I'll do that later. Okay, so let's take a look at the homework, the very first question in the homework. See if we can answer it with what we know. I mean, we can always consult other sources. So take an educated guess. What portion of the electromagnetic spectrum can our eyes detect? It's kind of a tricky question, but if you look at the electromagnetic spectrum, it very clearly states what is it that we can see. We cannot see X-rays, right? I mean, we can see an X-ray radiography, but not the rays themselves. And we cannot see radio waves. We also cannot see UV light. So that only leaves visible light. It's almost like, well, yeah. So not a terribly complicated question. Now, if you really needed the place to look for that, you just go back to the book and look at the electromagnetic spectrum figure. Okay, let's see. Now, here's a mathematical question. Unfortunately, I did not delete it, so I want to address it right now. I did mention today that the wavelength is inversely proportional This is an important concept, by the way. To the energy. We're going to call it the frequency. Now, wavelength in the book uses a Greek letter from the Greek alphabet known as lambda. So that kind of weird inverted P sign, I don't know, inverted Y, I don't know what to call it. And the frequency is this also weird V. With a little tail. And the term inversely proportional. This is somewhat counterintuitive because mostly in life we deal with direct proportionalities. Your grade in this course is going to be better with more effort, so more. That's a direct proportionality. What doesn't make sense sometimes is to say, well, your grade in this course is going to be higher if you work less. That would be an inverse proportionality. That is really not true. But it happens to be true in science on occasion. Okay? So inversely proportional means that when this gets bigger, this gets smaller. And when this gets bigger, that gets smaller. It turns out that there is an equation that describes that. And that is actually in the book. I'm going to give you the answer. So it's going to be that answer. When you see a letter C in chemistry, most of the time it means the speed of light. Okay? So here, the product of the wavelength times the frequency of that same electromagnetic energy equals the speed of light. You didn't know that because I didn't explain it, but I'm giving you that right now as an informational piece. And here's a brief explanation of that. So please use your attempts and use this as a learning tool. I'm not going to be giving you problems in the exam dealing with frequency and wavelength. But it happened to have escaped my notice and it stayed there. Any questions about that? I don't want to minimize the importance of it, but it's not terribly important for this course. I also meant to delete this one. I don't want to give you more math. So let me do the following. Don't start the homework until tomorrow. I'm going to delete these questions. I'm just going to get rid of them because it's not needed for this course. You already know how to manipulate many equations, so I'm going to delete all of the quantitative questions. Let me just skip it. Okay, this one is easy. All you do is you look at, let me go back to the book, and the way to answer that question is to go to the electromagnetic spectrum. I believe it was in page 120, right there. Let's go back to the question. Oh, where is it? Which of the following type of electromagnetic radiation has the longest wavelengths? So let's look for the longest wavelength among these three choices. If you are doing this live, then you're going to see different ones. So infrared, radio waves, cell phones. Longest wavelength. So let's go back to the book. So AM, FM, right there. Cell phone, right there. So that's actually shorter. So this is longer. And what was the third one? I forgot.
Heating wave? Was
Infrared? Infrared, right? So infrared is somewhere over here. Yeah, the heating lamp, infrared. So short wavelength, little bit longer, longest. So the AM, FM radio wave is the longer wavelength, the more distance between peaks and peaks. So that's what we're going to answer based on this graphical cue. Doesn't even give us feedback. Oh, we are, oh my God, I'm 5 minutes over. You guys, you're so kind. Okay. No. I wish you would have stopped me. Okay. I'm going to abruptly end it up right here. We'll see you Thursday. Don't get late to your classes. I do have a class at 11 too, so thank you, you guys. Thanks for your kindness. Oh, man. Oops.